Уважаемые студенты, уважаемые профессора, преподаватели, коллеги, у нас сегодня в гостях известный профессор, преподаватель университета Минью, Португалия, президент Европейской ассоциации по контролю качества мостов и сооружений Евростракт, вице-президент Международной ассоциации по проектированию мостов и инженерных конструкций José Matos.
So, good morning to everybody. First of all, I'd like to acknowledge the warm reception from St. Petersburg University. And it is a pleasure to be here with you and to share some of the outcomes that was a result of almost 5 years of work and coordination of European cost action. And for those that do not know what is a cost action, and I would like to start from here. A cost action is a European project funded by European Union, but also that wants to cover the synergies with other countries, neighbor countries and other countries. And it is a project that mostly funds networking. So we decided a topic relevant for Europe, and in this topic they say, no, we need to invest here, and we will invest for different stakeholders, from academia, from designers, from construction, etc., to meet in different countries in Europe and to discuss this topic and to develop more and to try to standardize and establish guidelines for the future in the topic. I was fortunately, I was successful convincing European Union about the importance of the quality control of bridges. I'm going to speak a little about it. And I was also successful and was very happy, although it was a very hard work, to manage a big team with people from 37 countries, speaking different languages, with different cultures. It was very profitable for me. I think it was profitable for everybody, for the European Union for sure, for Cost Association for sure. And I hope that in the future, the outcomes of this cost action could be used not only in Europe, but all over the world. I know that there are some countries that are implementing now some of these guidelines, and I hope that in the future other countries will do so. So, okay, hear me? Or I need to be here? You can hear me? Can I speak like this? It's okay? Perfect. So, okay. Why? There are some places here. Come on. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. So, why quality control and why this is important? This is not something only from Europe. This is something from, I would say, from the countries that built a lot in the last years. We call in the OECD, we call these the mature countries in terms of infrastructures. So those countries that built a lot in the last years, and mostly, I don't know why, but we use a lot concrete. And we all know now that concrete has some durability problems. I'm not sure if this is to give some work for civil engineers in the future, that we use this material. But concrete is representing in Europe around 85% of the bridge construction. And but not only concrete, steel and timber are materials that face degradation, decay, due to loading, to exposure, and sometimes even the material that we are using can have reactions, chemical reactions and others, and some decay. The problem is that we have big decay processes, and even worse, because if we build everything on the same time, in a very short time, the same infrastructures, as you can imagine, the damage processes are the same, so the same infrastructures will have the same decay problems on the same moment. So what's happening? We have to focus on new structures and design, but we need to know and take care of the heritage of our existing structures. And we have a big problems with decay. And the owners don't know how to deal with it. This is even worse. This is even worse because society, we want more and more. Now we speak in Europe and all over the world about the no maintenance infrastructures. We want something that these infrastructures do not have any more maintenance and any more problems always available, so that everybody could go to home or to the work or to the university without any rush, without any traffic. So public demands are very high. Expectation is also very high. As I told you, the no maintenance is an expectation. We need to now to look for materials that do not need any maintenance, but this is something in the future. So combining these three ingredients, it makes the work of our owners very, very hard. And this is even more hard because the resources that we have are very scarce. OECD says that each country should invest around 3 to 4% of the GDP on the maintenance of their infrastructure. We are very, very lower than these numbers. So we have small money to do a big job. And how can we do that? We need to have efficient systems that will support the decision makers, the owners, on prioritizing their maintenance investments. And the decision of this is only supported on indicators. And what are indicators? Indicators, I believe some of you already went to the doctor, and some of you already did some tests, blood tests, air tests, X-ray, everything. Sometimes we use a non-destructive tests. Sometimes we use only visual inspection. Sometimes we put some machines during one day or 1 week in order to measure our behavior. With the bridges, it's the same thing. The existing bridges, we are existing people. These are existing bridges. So with existing bridges, we need to take indicators, and these indicators are very important because these are the information that later will support the owners on taking the best decisions according to the maintenance of their infrastructure. So if we have wrong data, we're going to have wrong decisions at the end. So we need to have the right data with a very high quality level. And this is even worse because most of the data that we get is from visual inspection. And you all know that visual inspection is made by people, like you and like me. A lot of these people is not experienced people. Sometimes they are even no civil engineers. They are technicians, but not with too much experience. And sometimes with a lack of training programs. And this makes the data from visual inspection not too much liable sometimes, or in a lot of times, unfortunately. We know that in some occasions we can use NDT tests, which is very good and make this data more precise. And also sometimes we can implement monitoring systems. So in terms of accuracy of the data that we are obtaining. Based on these three, we get an indicator that will give us the performance of the bridge is okay or is not okay. And this is only able, you can only assess if the performance is okay or not if you have goals to achieve. If this bridge is achieving these goals, then it's okay. If it's not achieving these goals, then it's not okay. And then we need to do some investments on interventions, maintenance, etc. So we need to have performance indicator that will compare with the goal, and based on that, we'll do what we call the quality control plan or the decision making. So these are some of the management systems that you can see all over the world. All management systems, more or less, they are data warehouses, and they do not have any kind of decision making, and they simply put the data that is collected from the performance indicators in the database, and some of them do some forecasting, some no, but it's what they have. And there's a big dispersion after analyzing these systems. In Europe, there is a big dispersion on the way you assess this data, and also there's even a big problem, because who takes the decisions? If I'm the owner and I'm going to decide about my networking, is very far away from the person that is analyzing the bridge, evaluating the bridge, and assessing. So the civil engineer is very far away in most of these countries from the decision maker. More and more the decision maker is or a politician or a manager and the civil engineer and technicians, they are very far. So there is a big gap between who takes the data and who decides. So we need to have quality data, and we need to have a standard way of doing the quality control of our bridges, of acquiring the data, of comparing with goals, and taking decisions. This is more or less the objectives of this European cost action. The big objective that we had was to develop a guidelines for the establishment of quality control plans in road bridges. This was the big objective, because we want to have standard guidelines in Europe for everybody, at least some recommendations for everybody. And this was the big goal. Of course, there were other objectives. One very important objective is, and this is related because we have 37 countries, each one speaking its own language. So we need to have a common terminology and a common glossary. But I will say that the big objective was to have guidelines and recommendations for the quality control of bridges in Europe. These are the working groups that take part of this cost action. These are the main milestones or outcomes that came from each working group. If you go to the website of the cost action, www.TU1406.eu, but later if you want, I can share this with you. But you have all these reports there. It's completely open. You can assess, and you can do a further study on this matter if you wish. These are the 37 countries that were directly involved in this cost action. And there are other countries, like Russia, that made a accompaniment of what we were discussing and what were developing inside this European cost action. We have people from university, a lot, but we also have people from owners, from consultants, designers, from institutes. So we have all stakeholders represented in this action. As I told you, we need to speak the same language. We start to collect all the documents from the 37 countries documents which were used for doing the bridge inspections, what documents are being used for doing bridge inspections and bridge classification in terms of condition and so on. How is the bridge being classified? How are these documents being used? After collecting these documents, we did some screening, and after doing the screening, we took the main terms, the most relevant terms. And then we start to discuss each term at the 37 countries level. We did translation to each country, even if to check if everybody was okay with the translation. And we established a definition for each term. Here you have a definition of what it is performance indicator. But we need a definition of performance goal, quality control, reliability. The most important terms were defined. Another thing that we did, we need to decide what level of analysis should we do. Because academics mostly are focused here. Academics, they are analyzing a piece of concrete, a beam. It's what researchers are focusing on. Owners, decision makers are focusing here. They have a network with many bridges, 5,000 bridges. How should I manage these 5,000 bridges? And the problem is not the landmark bridges, because those suspension and cable stay bridges, we have monitoring system, we have very strict accompaniment and so on. The problem is the common bridges. These common bridges that are more represented in our network, how should we manage them? Because there are not enough money to manage these bridges. And owners were more focused here, and the researchers were more focused here. So we need to do this to bridge the gap, and we have to start on the component, then from the component to the system level, which is the bridge level, and from the system level to the networking level. So this is the 3 level of analysis that we did inside this European action. Then we start to speak with the owners, and we said, for you as a owner, what is important in terms of your network, and what are your goals? And one of the goals they have is, I want to minimize my cost. This is the first goal. If you speak with all owners, the first thing that they say is, I want to reduce costs. I want to have lower budget in the maintenance activities, in the interventions of my bridges. So minimize cost. The second thing that he's worried is minimize the delay for the users. And this is more important in PPP contracts, where the level of traffic is inside the contract model, so for the private owners, but also for the public owners it's important to minimize the delay, because this is a kind of image of the way the owner is taking care of their heritage, of their existing infrastructure. So minimize delay or maximize availability of my infrastructure. Minimize environmental costs, to be honest, and it's a pity, but no one cares, or it's not relevant as a goal. And another thing that is very relevant as a goal is to make our bridge reliable. And when I speak about reliable, is that the bridge is fulfilling the performance limit states, the ultimate limit states and the service limit states that all of you learn in the classes of civil engineering, the shear, bending, torsion, everything. So ultimate limit state and service limit state, vibration, deformation, etc., crack width, etc. So this is reliability. Is my bridge able to fulfill the performance limit states or not? And another thing that owners are also worried is about safe. Because a bridge could fulfill the performance limit state, but imagine that there is some problem in the expansion joints, and expansion joints do not affect the limit state of the bridge, but may affect the probability of having an accident on that bridge. Because when we go with the car, if the expansion joint is not in good conditions, there is possibility of an accident And this is very bad. So the owners want also to reduce the likelihood or the probability of accidents, so they want to keep their bridges in a safe condition for the users. And also their bridges reliable in order to fulfill the performance limit states. So in order to achieve these goals, we need to measure some indicators, like with the X-ray or other. We need to measure indicators from the bridge, from the components of the bridge, or at the networking level. We need to measure these indicators, and each one will give us how much are we achieving or not the goal. So, are we achieving this goal or not? So we need to have measurements to determine if we are or not. And also, as a owner, I can do strategies. I want to invest a lot in interventions, so I'm going to invest in my first 5-10 years in interventions, and then I'm not going to do nothing. Or I can say, I'm going to invest in small interventions during the lifetime of the bridge. During 100 years, I'm going to do small interventions. Or I can say, I don't want to do any interventions, I'm going to leave the bridge until collapse. It's an option, it's a scenario, it's an alternative that the owner needs to shake. And according to the different alternatives, during the lifetime of the bridge, we are going to have different values of these indicators, and we are going to evaluate if we are or not achieving the goals. So, we define in this cost section 4 relevant, what we call 4 goals, most relevant goals. Costs, availability of my bridge, safety of the bridge for the users, and reliability of the bridge. Reliability is what you know. What you don't know is the safety for the users, is the availability of the bridge for the users, and it is the costs of my interventions. Because reliability is what we learn in the school, in the civil engineering school, and so on. How we assess reliability? We go to the bridge, we do a checking, we can assess, we can do a numerical model, we can do load testing, wherever. We can assess the reliability. How we assess the safety? We need to check if my expansion joint is okay or not, if my safety guard is okay or not. I'm going to assess, and I say this bridge is safe or not. So today I'm going to the bridge, and I know how it is the reliability and how it is the safety of the bridge today. These 2 KPIs. Then I can do some projections. I can do some forecastings. I can use what we call the damage models, the damage processes. And I can say if the main damage process here is corrosion, so in 5, 10, 20 years, the bridge will have this reliability that will decrease. In 5, 10, 20 years, the safety of the bridge, the safety for the users will also decrease because the expansion joints have some material and some loading and unloading due to thermal loads and so on, and after some years, it will not work anymore. So I need to do interventions, and I need to have planning, alternative scenarios. And for my interventions, and for each scenario, I'm going to have different costs. So according to my scenario, in the long term, I'm going to have different costs. And also, according to my scenario, in the long term, I'm going to have different availabilities. Because if I'm doing a lot of interventions, for sure, the delay and the traffic demand will be very high. Because the bridge will never be always available. I am going to do an intervention here, the next year in another way, the next year in another way. If I'm not doing any intervention, okay, during 5, 10 years, it's okay, the bridge is full available, but after some years, the availability will be reduced also due to damage process. So I must say that while these 2 you can determine today, the costs and the availability it comes from the scenarios that you are going to generate. So these are a definition of these KPIs that I already told you. Safety, availability, costs, and reliability. And you can plot these graphs or these plots that show you how from 1 to 5, where 1 is very good condition or very good availability or very good safety or very good cost, so low cost, and 5 is very worse. So from 1 to 5, you can classify your reliability, your availability, your cost of your bridge, and you can do these kind of plots. Okay? This should. Okay. So these were the KPIs that for the owners in Europe are relevant to achieve the goals. So maximize reliability, maximize availability, maximize safety, and minimize economics. These are the KPIs and the goals. And as I was telling you, some you can do in a snapshot, reliability and safety, because you go to the bridge, you take a photo of the bridge, and you can take measurements and evaluate the reliability and the safety. Others, you need to do projections. You do it in a forecast. So you need to forecast reliability and safety, and based on that, you need to have different scenarios, and according to your scenario, you're going to have more or less availability or more or less costs. This is the quality control framework. So you have a performance value that comes from your observations or from other data, which is, these observations are supported in the damage process. Always there is a damage process that depends on the materials and so on. And the damage process will be the result of the evolution of this indicator with time. And based on that, you can calculate the key performance indicator, so safety, reliability, availability, and costs. It's not. Okay, I think it's. So this is an example of a bridge in Serbia. This bridge is a frame bridge, reinforced concrete, was built in 1963 and widened in 1977 with an average daily traffic of 10,000 vehicles. You can see here the old part and the new part, the widening. The widening was due to the increase on the demands on traffic. And this is the structure of the frame bridge you can see here. The first thing that you need to do is preliminary work, what it is. We need to collect the drawings and the material that we have. Unfortunately, most of the owners do not have drawings, do not have any materials from a lot of bridges. So this is a problem that we face in reality. But we can try to collect as best as possible. And in this bridge, we didn't identify any weakness. Of course, there is a problem in the joining between the old deck and the new deck. And also, there was a traffic demand on the loading, and we need to calculate what we call the reliability index for the new traffic demand, and considering that the bridge is not damaged. So what we do, we take the bridge system, we compare loading with the resistance of this system, very easy, and we can calculate what we call the reliability index that gives us the probability of my bridge of fulfilling or not a specific performance limit state. In this case, we evaluate two performance limit states. We evaluate a performance limit state of shear, and shear can happen in this region or in this region, and we evaluate a performance limit state of bending. And in order to have a bending collapse, you need to have a plastic hinge here, a plastic hinge here, and another plastic hinge here. So from these two, The critical one is bending. And for bending in this stage, we determine that the reliability index without any damage, no damage, on this bridge is 3.8. If you want to know more about reliability index and calculation and so on, I can also exchange some material with you later on. After doing preliminary work, we go to the on-site. On-site, we are going to do inspection. Inspection by components, but we are doing a different inspection. We are doing inspection on the places where there is the probability of what we call the vulnerable zones, the risky places. We are looking for these places in the bridge. So we are looking in this area, we identify a small crack here. We are looking in this area, identified some corrosion, also in the connection between the two slabs. And also, in order to evaluate the safety of my bridge to the people, to the users, we need to evaluate if there is any kind of road beneath the bridge, and there is one small road. And also, we evaluate the safety guards, and you can see here, the safety guard is not in a very good condition. So the safety guard is not in very good condition, and they may have some concrete chunks falling down the road that can also provoke any accident for the user. So the bridge is not in very good condition for the safety of the users. It's not too bad, it's not very good. And in terms of reliability, we identified some pathologies. So take into account reliability. So today, in a snapshot, we identify we identify these pathologies, and based on the identification and inspection that we did, we determine a reduction on resistance of 10%. Okay, so this is what we determine from my inspection, and then I can do this kind of plots where I compare the reliability index with the probability of achieving a performance limit state, and this is my initial reliability, 3.8, and I determine a reduction of 10% in my resistance of the bridge. So with a reduction of 10%, I'm going to have a reliability index today of around 2.9. So then I define different ranges from 1 to 5 for reliability, and I know that today my range, my classification of reliability is 3 from 1 to 5. With the safety, we can do it also qualitatively, based on expert knowledge, experiments, and so on. And in this case, we classify from 1 to 5 the level of safety of my bridge as 2. So it's not too bad. You can see here the application of the quality control framework, where you have the elements, the deck, the material, the age of the construction, the failure mode that is in evaluation, so if it is a bending or shear, in what vulnerable area are we evaluating the damage. This is the damage process and the pathology that we evaluate, if there was a crack and in what area, the spalling and so on. The classification of reliability of 3 that we assessed before. And the same for the safety. We identified some spalling in the concrete, and also some broken safety guards, and from 1 to 5 we give to the safety. So in a projection we can also check how it's going to evaluate according to the damage process, how is going to be the evolution of my reliability. And then I go to the availability, which is the one that I need to do scenarios and check the availability. But the availability should be studied in a network basis. So if my bridge will be blocked, what will be the impact for the network, for the traffic flow? So I need to know where is my bridge, I need to know the average daily traffic, and based on that, I know the costs of being unavailable this bridge. Intervention costs the same thing. I know the intervention costs, I do different projections and different scenarios, and I can calculate the costs of my interventions. So, as I told you, reliability and safety you can assess today. Then, based on the damage process that is changing the reliability and the safety, you can do different scenarios of maintenance intervention, and for each scenario, you have different costs and availability. So this is the plots that you obtain. This is the reference scenario, which is doing nothing. I let my bridge going to collapse. And anytime the bridge collapses, I need to build a new bridge. So my costs will be very high. Anytime the bridge collapses, the bridge will be unavailable. So the unavailability will be very low. And anytime the bridge collapses, the safety for users will be, of course, very, very low. I have another scenario here, which is a preventative scenario, which means I do not let the bridge achieve a reliability higher than 4. So 4 is my limit. Anytime it achieves 4, I do an intervention. So the costs are here, identified. The availability is also identified, and the safety as well. So this is very important, because if you want to compare the different KPIs, you need to use the same units. And the same units, in this case, the only unit that can be used to compare is money. Everybody knows what is money. The owner knows what is money, and the technician knows what is money. So everybody is speaking the same terminology. And how you convert the KPIs in money? So, intervention costs are money. The availability, you know, for any delay on the traffic, you know how it costs for the owner. This is possible to quantify, or through a PPP model, contract, or you can quantify the delay. So you can convert availability into money. The reliability of the bridge itself, you cannot quantify into money. But if you calculate the reliability, multiply by the consequences of a failing, then you are introducing the concept of risk, and risk is equal to money. So if you multiply the reliability by the consequences, you can convert into money. And the safety, the same thing. If you multiply the likelihood of safety of my bridge by the consequences of an accident or whatever, you can convert into money. So you can, for these 4 KPIs, you can range them by money, and you can do it qualitatively or quantitatively, qualitatively from 1 to 5, and based on that, you can use what we call the net present value theory, which is, according to my different scenario, do nothing or reference scenario, what is the today money that I'm going to spend for these 4 KPIs. So, using the net present value, that depends on the interest rate of each country and so on, I can convert today, and I can decide today what is the best scenario that I have. So I can use this kind of algorithms, and I can compute for today, and for the 4 KPIs, I can compute from 1 to 5 today again, the different plots that I showed before. And the scenario that has a larger area, which is close to 1, is the perfect scenario. In this case, the perfect scenario is the preventative and not the reference one, which is the do nothing. So, we did several case studies, from the 37 countries. This is also provided in the website of the action. I'm on time, right? Okay, so because I need only 5 minutes. Yeah? Okay. So, we did several case studies, and this one that I want to show you is one from Portugal. It was a work that was developed jointly with a colleague from the University of Cyril and Methodius in Skopje, in Macedonia. And what we did, we started to do the preliminary work to study the bridge, the case study. In this case, it was an arch bridge made of concrete. And this bridge belongs to Infrastructures of Portugal, which owns most of the bridges in Portugal, and was submitted to two inspections, and one intervention in 2010. And here is some of the tests that were developed in this bridge. The bridge, as I told you, is in Portugal, located in the northern interior of Portugal. This is some images of the bridge. It's a road bridge. And then another thing that we need to do is to study the structural scheme of this bridge. So this bridge is a simply supported deck arch. You have here a slab, a concrete slab. The slab is supported in spandrel walls, and the spandrel walls are supported in a concrete deck arch. It is simply supported into sections, here and here. And these are the main elements that are constituting this bridge. So, then we went through the inspection, and during the inspection we identified in the different elements that you can see here, some are main elements, some are secondary elements. We identified different pathologies. So each element has a different pathology. And you can see here from wet spots to airline cracks and so on. These are more pathologies that we were identifying. And then we did the same as we did with the other simple bridge, which is what are my performance limit states and what are the vulnerable zones. So in this case, the performance limit states were three, were a high moment region that you can see here. Here are negative and positive moment regions. High compression region. Here you have big compression in the walls. And also we have a service limit state, which is high deflection at the midspan. These are then the critical sections that we have, or the vulnerable sections that we have of my bridge. And then we need to do the match. Where is my pathology and the location of the pathology in these vulnerable sections. So if it is or not related with any of these limit states, bending, shear, or deflection. So these are the pathologies that we identified, and we connect also the pathologies with the main elements. If it is on the slab, if it is on the arch, or if it is on the wall, spandrel wall. Then we applied again these tables that says what is the failure mode, bending, compression, what is the vulnerable areas from these areas, that were identified the pathologies, what were the damage that were observed, what were the damage process related with the observation, if it is a symptom or if it is related with the reliability KPI, and we had given a classification from 1 to 5 to each of these pathologies according to the failure mode. So we took the worst scenario, which is corrosion that we saw through surface cracks on the walls in B. So here we saw some cracks due to corrosion. And we took reliability of 4 today. The same for safety. We saw some problems, some corrosion in the railings, and we took 2 for the safety KPI from 1 to 5. Of course, we can do it also quantitatively, not qualitatively. Here is purely qualitatively, but here is quantitatively. We can do a numerical model. With this numerical model, we can define the limit state function. Based on a limit state function, I can calculate the version reliability, so the reliability without any damage. And then I can say that based on my observations, I have 8% of reduction in my resistance. And with this 8% of reduction, my initial reliability of 4.26 will decrease to 4.17. So this is how we can calculate it numerically, quantitatively. Then we can use different scenarios. So we need to fix a model, a degradation model, that gives us the evolution of the reliability with the time. And then we need to fix different scenarios, do different corrections, or do some prevention. We need to attribute values for these scenarios and for the different interventions. If you have crack sealing, waterproof, and so on, what are the effects of these interventions? If you have a deck wash and so on, what are the effects? You can do it quantitatively. You can quantify the costs of your corrective and preventive scenarios. And then you can draw this kind of plots. This kind of plots starts with the today beta, today reliability, do nothing, which is this forecasting. The bridge will last 58 years if I do nothing. If I do a corrective interventions, I can take the bridge longer. If I do some preventative, so it will achieve 5 after 50 years. So these are the different scenarios. And you can see here the range from 1 to 5. This range is from Eurocodes. Eurocodes already give us the limits, the thresholds and so on, in service, in ultimate mid states and so on. So we can do this range. And you can say the jumping on the reliability from 1 to 5 during the years. So this is the evolution, do nothing, corrective and preventative scenario. For each scenario, I have different costs. Do nothing, I have to build a new bridge. Corrective and preventative. Availability, the same thing. Safety, the same thing. And then using the net present value theory, I can convert these 3 scenarios for the 4 KPIs in these plots and take the one with the larger area, which is, in this case, the corrective scenario. So for this arch bridge today, the best scenario is the corrective because it presents the larger area, as you can see here. So the cost action didn't finish here. We started later European Association for Quality Control of Structures. We are applying this to all other kind of structures. You can see here, this is the aim and the objectives of the association. We extend it to other structures. It is in the website. You can take all the information. This is the kind of things that we are doing, training courses, conferences. So you can register, you can join. These are the contacts. And the next conference will be in 2021 in Italy. And soon we'll be providing some information about it. So thank you very much and for hearing me.